Okay, so we are ready to begin. I wish everyone welcome to our sixth meetup. This time we have Maarten Mulders with us, and he's going to give you a walkthrough to GraalVM and how to implement a custom DSL and language. We are javaBin. We are the Norwegian Java user group. We have 80 different regions throughout Norway, and we run monthly meetups and other events. So we have a lot of interesting talks coming at the upcoming weeks. Please follow us on Twitter or join our meetup to see what's coming up. My name is Darvish. If you have any questions, please use the comment field in YouTube, and we will make sure to get them answered for you in the end of the meetup. So you can just use them, and we will make sure that Maarten will get the questions in the end. So Maarten, welcome, and thanks for joining javaBin Online.
Thank you, Doris, and thank you everyone for attending today. My name is Maarten. I work at a Dutch consultancy company called InfoSupport. We are really passionate about technology. We think technology is awesome sauce, which is why we actually created our own awesome sauce with a nice logo for it. And one of the things that I learned about actually back in 2018 when I attended JavaZone 2018 as a speaker, I attended 2 sessions on GraalVM. One was by Chris Talinger, which was about the compiler replacement project in GraalVM. And the other one was by Oleg, and it was about the fact that you can actually run different languages than Java on the Java virtual machine. And we're not talking Kotlin or Scala, we're talking JavaScript or R or Ruby. And I got curious by that talk, really curious. I was like, okay, it's cool that you can run JavaScript, but hey, we've got Node.js already. Now, what if I wanted to run any other language than that? How would you actually make that happen? And that's where the journey started. And the outcome of that journey is something that I want to share with you today. So let's see, I should share my screen with you because I obviously have some slides to go with this story. Yes, so we're going to build a DSL on GraalVM today. Just to have an idea for myself, usually I would ask you to raise your hands. So I have an idea of what you as an audience know about the subject already, but yeah, you raising your hands in your attic just as I'm standing here in my attic, that's not going to help us really much. So please go to Slido, scan the QR code, or just go to slido.com on your phone. Use the event code that you see here, and be as kind to answer a simple question for me. What's your experience so far with GraalVM? Ranging from, well, I've heard about it, to, hey, the talk that you're actually giving, I could have given it myself because I did the same thing. I'm curious to see how that is in this group, how much experience you have already, and it will help me find the right level of how deep we should go in this talk. So before diving into GraalVM, I first want to quickly go through the concept of domain-specific languages. So a domain-specific language, what is that actually? A domain-specific language is a language that can be interpreted by a computer and that it's targeted at a specific domain. And ideally, the language is also targeted at the users in those domains, the people that actually operate on that domain. Let's go through a few examples. So for instance, here we have a language which is targeted at working with databases. And the constructs that we see in this language do make sense to people who operate on daily basis with on a daily basis with a database. So they know that they can select rows from a table and that they can group these rows and, well, all that kind of stuff. And if we want to operate on a database, we use SQL, in this case SQL, to do that. And that this language is not good for anything. You can build anything with SQL, but if you want to do something with a database, SQL is definitely going to be your friend. Second example is gherking. And some people say, hey, this language, this is about banking, but no, this language is not about banking. This language is about specifying the behavior of a computer system. And not only specifying behavior, but it also doubles to actually verify this behavior. Gherking is often used to write automated tests that you can run against your system that you have built to verify that it behaves in a certain way. This one I saw at a conference a couple of years ago. It's not very well known. It was also talk about DSLs, and they had this example company of a wolf and a sheep that wanted to do a transportation company. And well, the transportation company actually ships cabbages and sheep and from one shore to another, but they wanted to make sure that none of the employees of the company would eat each other or the cargo. It's a classic puzzle. How do you solve it? Well, they wrote a DSL so that they could actually simulate, hey, if we do it in this order, will it work or will it not work? Now, this domain-specific language is really focused at a very small domain. It only worked for this specific fictitious company, and it was built upon Scala, which you can recognize a little bit in the syntax of the DSL, but that doesn't matter. It doesn't have to be a problem as long as the domain users can actually write scenarios for transporting cabbages and sheep. It can be a perfect example of a DSL as well. And the last example that I want to share with you today is this one. And this is a very specific language. You might argue it's not a domain language, a domain-specific language. This language is called Brainfuck. And it's traditionally written without any comments or white space or whatsoever. So just in its classical form. Its domain is twofold. Excuse me. On one hand, it's impressing your friends that you can actually read and understand this and write it. And on the other hand, the domain for this language is making your head explode, because the language in all its simplicity can be very hard to use correctly. As I said, the language is best written without any kind of comments or formatting or white space, but you can do so because anything that's not part of the language is automatically a comment. And this is the same program as we saw previously, but now it has been commented so that we can actually more or less understand what it does. Most important thing, it adds the numbers 2 and 5 together. And it does so by storing the number 2 in a slot, moving to another slot, storing the number 5, then starting the addition, and finally printing the outcome to the standard out. The language traditionally works with one piece of memory, 30,000 positions long, each consisting of 1 byte. So the memory model might well look like this, somewhere halfway program execution. In the upper row, we see the indices of the memory. In the lower row, we see the actual values, and we see that the first position contains the value 2, the second position contains the value 5, and the first position contains the value 3. And in addition to that, there's one pointer that actually moves back and forth through the memory area to actually make sure that you look at the right value. So you have one pointer that determines the current value you operate upon. The language has 8 commands in total. The plus sign obviously means to increase the value at the current location, while the minus command means to decrease it. The dot means print the current value to standard out, while the comma means read 1 byte from standard in and store it at the current location. Using the square brackets, we can implement jumps. So if the pointer points at the memory location that holds the value 0, and the current command is a open square bracket, then it will make sure to jump after the matching closing bracket. And likewise, if the current value is not equal and your current command is a closing square bracket, it will jump back to the matching opening square bracket right after that one. And finally, we have the less than and the greater than commands, which just mean to move the pointer left and right through the memory. That's the whole language. That's all there is to it. You're now officially a Brainfuck expert, if you understand this. And this is not particularly hard, if you ask me. Now, the hard part is writing a program in this small language. Funny thing is, you can write any language, any program in this language. It's Turing complete, as they say. Now, I recently came across this interesting remark. I think it was Venkat Subramaniam saying, well, a language that is Turing complete, I don't care about it, because if a language is not Turing complete, that means I can't even write any given algorithm in it. If a language is not Turing complete, it's just not a language that I could use for my day-to-day work. So we should go one step further, and Brainfuck actually is not only Turing complete, it's also considered a Turing tar pit, which is a subset of Turing complete languages, specifically created for those languages that, well, they can implement any algorithm, but it's not necessarily a good idea. Or put differently, it's probably a bad idea to do so. A tar pit, something that you can easily get lost in and drown in. So this is all we need to know right now for domain-specific languages. We'll stick with Brainfuck for the remainder of this session. And now it's time to look at GraalVM. Many of you say, I have heard about it. Some of you say, hey, I know this, I've used it to build native executables. A few people say I have run some other programming language like JavaScript or R or Ruby using GraalVM. So GraalVM is a research project by Oracle Labs in collaboration with the University of Linz, Technical University of Linz in Austria. And they describe the research project as a project to find one virtual machine to rule them all. Well, that's an ambitious goal. GraalVM, in fact, consists of quite a few things. One of the things that GraalVM encompasses is the GraalVM compiler. Start talking to Chris Tallinger, and he'll tell you all he knows about it, which is an awful lot, if you ask me. It's all about compiler optimizations and how the GraalVM compiler can actually outperform the standard hotspot compiler that ships with Java for many years. Fun fact is that the GraalVM compiler is, unlike the traditional compiler, not written in C++, but in Java itself. And another major part of the GraalVM project is a separate module called TRUFFLE. And TRUFFLE is what we will be using to implement our own languages. So right now you can already run Java on the Java virtual machine, of course. Using TRUFFLE, you can run, for instance, Ruby or JavaScript. On top of TRUFFLE, there's Sulong, which allows you to even run native executables written in C or C++. And you can run those on TRUFFLE and so on the Java virtual machine. But if you want to run your own language, you don't and implement it, you don't necessarily need, for instance, the GraalVM compiler. You could do without. You do need TRUFFLE, by the way. Substrate VM is the part that you've been using when you created native executables from your Java source code. And that's something that we're not going to use today. So this is an interesting one. This GraalVM compiler, you may not need it, but nevertheless, you could use it. And that's interesting because according to the GraalVM people, if you do use it, your TRUFFLE programs will run faster. Well, that's an interesting claim, isn't it? It will run faster by just replacing the compiler. Excellent. Proof. I want a proof of this. So I created a benchmark because I believe that numbers will tell us if it's true or not. I found this little program. There's actually a whole website dedicated to Brainfuck programs. And one of them is yapi.bf, which is a Brainfuck program, yet another pi calculator. That's YAPI. And it allows you to calculate pi for 15 digits behind the dot, 15-digit precision. I ran it through my Brainfuck implementation on top of TRUFFLE using the standard hotspot virtual machine, standard compiler. And on average, I found that I can run around 50, that every invocation of the program took around 53 milliseconds with a mean error of 1. Well, that's pretty neat. 53 milliseconds isn't that much. Then I switched to the GraalVM runtime, and I ran the same benchmark again. And my execution time went down to 45 milliseconds per invocation, still with a mean error of 1. This is approximately 10% faster, which is pretty good if you ask me. It's even a bit more than 10%. So I made the program a bit more complex, adding for more computational complexity by not calculating 15 digits of pi, but 45 digits of pi. The average execution time went up to 207 milliseconds per invocation with a mean error of 2. And running it on a GraalVM runtime, that 207 milliseconds per operation went down to 185 milliseconds per operation. Again, roughly 10% faster, and the mean error is still pretty low on 3 milliseconds. So I'm actually impressed by this because the claim, yes, it will run faster. Well, from this simple benchmark, I know it's a micro benchmark. There's a lot of disclaimers here. There's a lot of other things that may influence it, but still it looks as if the claim holds true. So much for the GraalVM compiler, because as I said, you can use it, but you don't necessarily need it. So what's this TRUFFLE thing? TRUFFLE is described on their GitHub page as an open source library for building a programming language implementation as an interpreter for a self-modifying abstract syntax tree. Now, the first part isn't that hard. It's a library for building a programming language implementation. So far, so good. As an interpreter for a self-modifying abstract syntax tree. And that's the interesting part here. So an abstract syntax tree is basically a representation of your program. And here we see a part of the Brainfuck program that adds the numbers 5 and 2 together. It's a tree-like structure, so there's always one root node. And it's abstract in the sense that all details from the source code are gone. So imagine you're building an abstract syntax tree from your Java code. You will not see whether or not there were curly braces following that if statement. And you will not necessarily see the names of local variables. It's just a slot. It's a memory location, but its name doesn't really matter anymore, as long as we'll always be referring to the same one. So there's a lot of details gone in the abstract syntax tree, and it focuses on actually executing the program that you wrote. Now, self-modifying in this context means that that TRUFFLE allows you to build an abstract syntax tree, and then whilst you're executing it, modify it. And this is what happens. Your program will start, for instance, using interpreted code, and it will jump between some nodes in the abstract syntax tree that are all interpreted. One of those nodes may delegate to runtime code, which is just code that ships with the Java virtual machine itself. But at some point in time, TRUFFLE may decide to actually optimize some nodes in the interpreted code. The interpreted code is the guest code, so as to say. And that code is then optimized into compiled into a highly optimized version of, for instance, the function X or Y. Oops. As I've written down there. That optimized code is really targeted at your runtime, at your processor, your CPU. So it will definitely have a very high performance, but it's not interpreted anymore. And just as from interpreted code, it may jump back and forth with runtime code and interpreted code back and forth, etc., etc. And the fun thing is that this optimization can happen at runtime and not necessarily only at compile time. And that's where the self-modifying stuff comes from. Now, self-modifying, that also sounds a bit scary. So let's at least hope that we have some mechanisms to control this. The trick that they actually applied here is called partial evaluation. And partial evaluation may sound tricky, but it's actually something that's already well known in the mathematical world. For instance, if you would ask a mathematician how to calculate x to the power of n, and to write a generic program for that, they might come up with something like this, which is just a rather verbose way, if you ask me, to say x to the power of n. Well, if n equals 0, then x to the power of 0 is always 1. If n is even, we could take half of n, calculate x to the power half of n, and then multiply that with itself. That's how you could rewrite the same formula. And if n is odd, then you can subtract 1 from n, recalculate x to the power of n minus 1, and multiply that with x. And given this, you can always evaluate x to the power of n for any given values of x and n. Now, what is partial evaluation? Partial evaluation says, let's say that we either know or assume that we know, for instance, that n is 5. If n is 5, then we can greatly simplify the above program, because we can just say, well, if n is 5, then x to the power of n is x multiplied with x multiplied with x multiplied with x multiplied with x, in this case. So our program is way simpler than it used to be. The whole branching is gone because, well, n is no longer a variable. It's actually a constant right now. And we can rewrite our program into a simpler form. And this trick makes formulas in mathematics simpler, and it can also make programs more optimized for your environment. So what we basically do with partial evaluation, we make assumptions about the data that our program is going to process. Now, I talked about an abstract syntax tree before. If we are going to model an abstract syntax tree in TRUFFLE, we code them as a POJO, a plain old Java object. There's a few things that we need to be aware of. POJOs always need to extend node, which is a class that comes from TRUFFLE. We have frame slots. That's a way to access our memory. And we have an execute method. And the execute method takes a frame, which is basically the instance of the memory that we're currently looking at, described by the frame slot. And the execute method is what happens if this node of the abstract syntax tree is actually being executed by the runtime. In this case, we look up where our pointer is currently pointing at. We look up the value of that location into memory. We increase it by 1 and we store it back into the memory. So that's a very simple node in our abstract syntax tree that will just increment the current value of the memory plus 1. And these nodes, you could instantiate those classes. They will form a tree of objects, and that is our abstract syntax tree in a TRUFFLE program. And now there's two things that we can do. The first thing is that we can do is we can create boundaries in our abstract syntax tree. Because this partial evaluation trick that I showed you previously will do all kinds of assumptions on the code that we run. But sometimes it doesn't make sense to actually perform this optimization. And that's where boundaries come into play. With a boundary, we can say, hey, TRUFFLE, it's all fine and good that you're doing this heavy optimization stuff, but please stop here. Don't try to optimize anything below this. So for instance, if you have a node in your abstract syntax tree that does some printing to standard out or to any kind of a print writer, you see here print writer, it's just the standard Java interface. It doesn't make sense to perform partial evaluation behind this point. The code in there is highly optimized by itself already. Going there and doing all this optimization and analytical stuff is going to take a lot of time, and it's not going to deliver any kind of improvement over what we have already. So we can actually tell TRUFFLE, hey, please refrain from further optimizing this part. The second thing that we can do, that's even more powerful maybe, is that we can define specializations. And this is a very specialized transport, I would say. A specialization allows you to give hints to TRUFFLE in what situations an implementation may be the best strategy. For instance, we could have a divide method, and we could say, well, this is a specialization, but this specialization only makes sense given this guard condition. We have a divide method. We want to divide the number A by the number B, but this specialization doesn't check if B is 0. If it is 0, it will obviously not work. But if we would need to do this in our runtime code, it's an additional check to perform. Instead, we declare a specialization and we say only if B unequals 0, we can use this specialized implementation of our divide method. Or another example, if we want to add two numbers together, the fastest way to do so is math.addExact, which will just throw an arithmetic exception if the outcomes is bigger than what fits into an integer. In that case, doing A plus B will work, but this also requires a cast because the outcome is long, and that's an expensive thing to do. Specializations are always executed in the order that they occur in source code. So TRUFFLE will at first try this implementation, and if it fails, it will switch to another specialization. So just to make sure, imagine we would add max value -1, and we would add the number 1. Well, we will at first invoke the do add no overflow specialization, which works just fine. We're good to go. Imagine that the next time we're adding max value +1. Well, that would throw an arithmetic exception because it doesn't fit into an integer anymore. And that means that instead, this second specialization will be applied, which is do add with overflow. And it will return a long, but that's more heavy in terms of computation. And then the third time, if we do max value -1 again, and we add the number 1, well, then the first specialization is now invalidated. It's no longer useful because it has failed us in the past, and TRUFFLE will stick with the do add with overflow implementation, which is more expensive to perform, but at least it works. Well, the other one is less expensive, but does not work. Now, this is very powerful, and you may imagine that using these kind of specializations when implementing a programming language can really give you a lot of performance benefits as opposed to having to do these kinds of checks every single time again. As long as your assumptions hold, you can use specialized implementations of your your AST nodes, the implementations of that, which allow for a better performance. And this also brings us to the question why GraalVM runs your guest language faster than a stock JVM. Imagine, for instance, we have an abstract syntax tree node somewhere that calculates the absolute value of a given number. Well, what we could do is we could actually have our assumption that any input that we see is just a positive number. We will only see positive numbers in the input. That's maybe a bit naive assumption, but it may well hold for a long period of time. And as long as the assumption is valid, well, implementing the apps function is very simple because we just return the input value that we got. Now, if there's one moment that we observe that we have a non-positive input, so a negative input, then we could use a special Graal construct, TRUFFLE construct, sorry, which is called transfer to interpreter and invalidate. That's a whole mouthful. What it says, we need to switch back to interpreted mode right now. We need to invalidate the assumption that brought us here. So the assumption that we will only see positive numbers in the input. And here we have the more expensive computation, which does -1 multiply with the input. Now, to a default hotspot JVM, this transfer to interpreter and invalidate is just a method call that does nothing. And to GraalVM, to the GraalVM compiler, this means something. And it knows that it should emit different code in this case. But because the hotspot does not know what this actually means, this transfer to interpreter and invalidate, it will also do that because, well, the semantics of the transfer to interpreter and invalidate method are unknown to the hotspot compiler. So that's where the little bit higher performance comes from. So now that we know all this, we can start investigating how we should actually implement our own language based on TRUFFLE so that we can run it on GraalVM. And the first that we need to do when we want to run our own language is we need to find a way to transform source code into this abstract syntax tree. Luckily, we don't have to reinvent this ourselves. This is a solved problem, I would say, because we already have many compilers and runtimes for decades. Imagine we have this piece of source code 734-692. Well, if you write it in your editor in Vim or Nano or Emacs or whatever editor you use, and you write it to disk, it's just a file, which is a bunch of bytes on disk. And by convention, we will display it as 734-692. But it doesn't mean anything. The first thing that we need to do, we need to lex our source code, which adds semantics to characters. And it will, for instance, say 734, hey, that's a number. It's not just the character 734, ASCII values, whatever. No, this is a number 734. The dash or the minus means something. It's a token that has a semantical meaning in my language, meaning a subtraction. And then there's 692, which is also a number. And by doing this, we convert our bytes, which happen to be readable as source code, into a sequence of tokens that have a specific meaning, semantics in my language. The next step is that we parse these tokens into a data structure that is often hierarchical, aka the abstract syntax tree. And in our case, we might come up with an abstract syntax tree that looks like this. 734-692, that's an expression. And the expression is actually a subtraction, which has two operands, two arguments, 734, 692. And of course, for those of you who are curious, the answer is obviously 42. Now, if you are going to write parsers and lexers, there's two things you can do. And the first thing I did when I implemented my Brainfuck on GraalVM was I used some regular expressions, because that's the easiest approach I knew for doing simple text processing. And since we have only a very small language in terms of constructs and whatnot, it would probably suffice. Well, as we all know, if you have a problem and you use a regular expression, then you often have one problem more. This is partially true, given the fact that Brainfuck is very small in terms of what the language consists of. You can get away with writing some regular expressions. If you would be implementing a more complex language, you would definitely need something better than a bunch of regular expressions. And what you typically end up using is something called a parser generator. For instance, Antler is a very famous one in the Java world, which allows you to specify the grammar of your language, and then Antler will generate a lexer and a parser for that language. And if your language is anything more complex than Brainfuck with its 8 commands, I would highly recommend not to write such a lexing and parsing yourself, but use Antler to actually generate that. It will probably outperform whatever you come up with, and it's probably easier to maintain than whatever you come up with yourself. So if you have that, you have a few snippets of code that allow you to transform your source code into an abstract syntax tree. The abstract syntax tree are some TRUFFLE classes with those annotations on it. You're already a good way to go. And there's just a few more things that you need to do before you can actually run your program on GraalVM for real. First, we need to know about the GraalVM updater, or GU for short. It's a little tool that comes with GraalVM, and it allows you to install components into your GraalVM distribution. Components can be tools or language packs. So if you have been using GraalVM to build native executables, at some point in time, you needed to do this GU install native image, which will look up native image in the GraalVM repository, which is hosted on GitHub, if I'm not mistaken. Will pull down some files into your machine and install them. And if you do not have your component published in this repository, you can also install a component from a local file. At the end of the day, a component is just a jar file. And in my case, it's something like Brainfuck 01 snapshot component.jar. So what does a component look like? Well, as I said, it's a jar file. And if we look inside it, we find a couple of things. We find a folder called metainf with a manifest, a special file permissions, and a special file symlinks. Permissions is a file that actually describes if any of the other files in the archive need special permissions, like for instance, BF might need an executable bit, so it becomes an executable. And symlinks describes if there are any symbolic links between files inside the archive. And the rest of the archive of the jar file is just a bunch of files that will get extracted into your GraalVM installation. And in my case, it's a simple shell script, BF, which will basically wrap around bf launcher.jar, which is a small command line program that uses brainfuck.jar library to actually run your Brainfuck programs. And at the end of the day, it's not a very big distribution. It's only 6 files divided over 6 directories as well. That's a coincidence, by the way. So packaging it up together, you have a jar file. You can install that using gu install -L. Now, if you want to use it, that's a 3-step to take, a 3-step approach. You need to prepare some source code. You need to prepare a polyglot context, and you need to evaluate your source code. Before we dive into that, let's first prove that it actually works. The proof of the pudding is eating it, isn't it? What we see here is a web application that I wrote It's just standard a Spring Boot with Spring Web and nothing other than that. And as we can see down there, it runs on an OpenJDK with GraalVM Community Edition 20 based on Java 1.8. Starting with GraalVM 20, you can also go for a Java 11 based distribution. I also have that on my machine, but I didn't test this program yet. So I wanted to stay on the safe side. And here I have some an input field that I could use to add to enter some Brainfuck code. As I said, anything that's not a command is automatically a comment. Anything that's not a command is a command. So the first line will blatantly be ignored. And when I run this program, it will output 7 as we would expect. It will tell me that it took 13 milliseconds, which is quick enough. So back to what we need to do to make this happen. We need to prepare our source code. We do that by somehow obtaining the source code, for instance, from the web form that you just saw, or from a text file on disk or whatever. And we use an API called the source builder. We tell the source builder that we expect to input some Brainfuck code. We could optionally give a file name, but yeah, we don't really have a file name because it's user input, so we just make something up. Next thing, we prepare a polyglot context. The polyglot context is basically an object that describes the context in which our program is going to be run. It's for the Brainfuck language again, and we want to capture standard out in our case. So we've replaced the standard out with a byte array output stream, and we build that context. And then finally, we evaluate our source code in that context. And we do so by invoking context.eval with our source. And that will actually, anything inside our source code, so for instance, the dot over there, that interacts with standard out will not interact with standard out, but with our byte array output stream over there. And that means that afterwards, we can actually capture the byte array output stream and see what's inside it. Every byte that has been written to it can be converted to a string. Whether it's readable or not, you don't know, but you can convert it to a string. And if you do that, you have basically run your guest language straight from your Java code with the same performance as the Java virtual machine can deliver to you. So that's all pretty good, but we aren't there yet because GraalVM gives you even more than this. GraalVM also brings a bunch of tools. And not only can you run your own language, you can even write your own tools. And that's particularly important because, as the original research papers from Linz University say, implementing a language is hard. You need to design the language. And once you finally came up with a design that works and that is correct and that is powerful enough, then there's no tooling for your programming language to be used. And users will be like, yeah, it's a nice language, but I can't even debug it. Or, yeah, it's a nice language, but I can't profile it. I don't know how it behaves at runtime. So GraalVM also brings you a bunch of tools to actually work with the language. And those tools are pretty generic. So they don't necessarily need to know about the language that you're building with it. Let's look at an example, which is the debugger. GraalVM comes with a built-in debugger. Let me see. I'm going to start the debugger, the program that I want to debug. And when I do that, it says to start debugging, open the following URL. In Chrome, there it is. So I'm going to copy that. Go to Chrome, paste that. And what we see here, I think is pretty amazing because now we have a Chrome debugger. Let me make sure that it's big enough. We have a debugger. We have the standard Chrome debugger that lets us debug our Brainfuck program. as if it were just JavaScript or whatever. So that means I can step. And as you can see there, it highlights the command that I'm currently executing. As you can see here, we can see the memory that we are working with. And we have already executed one plus command. So the first byte in our memory already has the value 0. And when I do one more step, it has the value, should have a value 2. That's interesting. Why doesn't it do that? Yeah, that's correct. I'm curious why the first slot still says it contains the value 0. Never mind. We'll just go on. And I can even say, okay, let me put a breakpoint over there and just continue execution until the next breakpoint. Wow, that jumped forward pretty quickly. I'm going to restart it because somehow the program misbehaved a bit. I don't know why exactly. Just to make sure. So again, like this, then like this. Yeah, this is better. And now the local variable is 7, and that's what we would expect. So we're actually debugging a Brainfuck program that runs in GraalVM on the Java virtual machine from a web browser. Well, if you were doubting, the future really is today. I mean, this is pretty amazing stuff, isn't it? And when the program exits, well, the debugger disconnects automatically, of course. So this is a tool that comes with GraalVM. The only thing you do is you start your program with -- inspect, and you add a few annotations to your abstract syntax tree to indicate, hey, this part of the abstract syntax tree is a place where the debugger could stop, or where the debugger could step over. Just to have a small example of that. Where is it? I think every command. Where is it again? Oh yes, it's instrumentable node. So if your node implements the instrumentable node, that basically says, hey, it can be instrumented by a tool such as a debugger. That's just a screenshot of what we saw already. And with Graal 20, they added more tools. So now there's also a coverage tool. You enable it with -- coverage, and optionally you can say -- coverage output -- coverage output file, which allows you to print logging of what part of your source code has actually been executed or not. Up until GraalVM 20, they said, well, we have a debugger and other tools. Well, you could implement them yourself, but with Graal 20, they added a few more tools, and this one is pretty amazing if you ask me. And it will just report either to standard out or to an output file. Maybe I have the detailed output file here living somewhere. No, the detailed coverage. You can even have a detailed coverage report, which will look like this. And it will basically report out on your source code and say, okay, if a line starting with the plus means it's covered, minus means it's not covered. And we can see that every line of our program has been covered. The tricky part is that in our language, the plus also has a meaning. So the report isn't particularly readable. But imagine we were implementing, for instance, a JavaScript or something, then this would be pretty useful report. So that's one of the other tools that comes with GraalVM. As I said, you can also write your own tools. Right now, there's a debugger, a profiler, and a coverage analysis tool. But you can also write your own tools if you want to. And to do that, you have the instrument API that comes with TRUFFLE, which allows you to attach to different types of events, like source code related events. There's a bunch of source code being loaded. Allocation events, which is basically, hey, we allocated some memory or we deallocated some memory. If the language starts, for instance, it's a thread, or starts executing your program, you can attach to that kind of events. And finally, if your program steps through its abstract syntax tree, you can also listen to that. And all these events you can handle in your tool by either logging something, collecting some metrics, printing stuff, whatever you like. So it's time to wrap up. We're almost heading towards the end of this session. My initial question when I visited JavaZone 2018 was, can you actually run any language on GraalVM, or is it just the few that Oleg mentions here? And the answer is a definite and clear yes, you can run any language on GraalVM. On the other hand, it may take some time to get there. I don't even know how much time I spent implementing this very simple language and how often I needed to reach out to the GraalVM people like, hey, I'm stuck. I don't know what to do. How do I solve this? It's certainly fun to do so. I mean, I learned a lot about how programming languages are implemented, what a parser is, what a lexer is, etc., etc. And in many cases, it will be just fun. But there are some examples of companies that are even able to make a business case out of it. For instance, I think the last 2 or 3 Code One events in San Francisco, Goldman Sachs had sessions about GraalVM, and they reported on their progress as they are re-implementing a custom in-house developed programming language, decades old. Hardly anybody understands how it currently works, let alone how it currently runs. But well, yeah, they run the bank on it, so it's kind of a big deal. And they're re-implementing that language on top of GraalVM. So that actually is profitable to them because it allows them to attract developers nowadays who are willing and capable of maintaining their in-house developed language that is already a few decades old. So if you want to go on this endeavor as I did, and if you want to take this journey, here's a few things that you really should take with you. First of all, please don't start writing your own parser. You typically don't need to, and you probably don't want to either, because it's a very hard job and there's very specialized implementations readily available for you already. So it's just not worth to put your time into that. I lost a lot of time there, so trust me on this one. And the second thing that I lost a lot of time on was designing my abstract syntax tree. So it is really a good idea, if you do this, to think about what does my abstract syntax tree actually look like? What are the nodes and how do I model it? If you go through this too quickly or you make mistakes, you'll have a wrong structure for your abstract syntax tree. And that leads to very hard to track bugs. For instance, at first I had 2 different nodes in my abstract syntax tree, one for jumping forward and one for jumping backward. And if those were not aligned, your program will run, but it will come with the wrong output. So you have a Brainfuck program, you run it online on a website, it gives the correct output, you run it on your own machine, it gives the wrong output. Very strange, very hard to debug, because debugging the AST is even harder. Turned out at the end that I should actually have jumping back and forth in one node, and that everything between those 2 square brackets should be child nodes. When I had that right, it was way easier to verify that my programs ran correctly. And as I did that, I learned that it's very hard to refactor this, because your whole abstract syntax tree is basically cooperating together. And when you change a bit of the structure of your abstract syntax tree, it's hard to get that right again. And it also costs a lot of time. If you want to learn more, you can find my current Brainfuck implementation on GitHub. Link is over there. And a few weeks ago, I actually started a follow-up project called Scheme for GraalVM, because I was like, yeah, it was fun and I want to do it again, but this time with a more complex language. So let's see if I can actually have the scheme language running on GraalVM. That's absolutely work in progress. It is far from complete, but if you are curious, you can check it out and see what you think about it. Dervis, I actually hope for a lot of questions on YouTube already. Can you share some of those?
Yes, thank you so much, Maarten. We have some questions for you. I will just start from the top. Let's see. The first question, Maarten, is, are the slides available?
I will make them available shortly after this session, and I will share a link over Twitter, of course.
Yeah. There's another question about, are the code available, but probably you can, that was already.
Yeah, the link is in the last slide, so that one's answered as well, I guess.
Yeah. There is one question. Do you think that the performance gain is also beneficial when running regular CRUD apps and API apps?
That's an interesting one. It might be, but I think regular CRUD apps or API apps, unless you're working at a company called Twitter or Netflix, you're probably not having their scaling problems. Actually, in this 2018 talk that Chris Tallinger gave about the GraalVM compiler, and Chris works at Twitter, by the way, he explained why the standard JVM was not able to meet their performance requirements. I think most of us are not at that level of scale. At least the systems that I develop as a consultant for my clients, the performance problems we have are not in the compiler. They're in database queries that are slow. They're in storage that's slow. They're not in the Java platform or the Java compiler. But if they would be there, it might help. On the other hand, I've also I've once attended a course by Kirk Pepperdin about CPU optimizations that you can do yourself by just rewriting your Java code, and that's actually, there's a lot to gain there. Trust me. So in general, I would say yes, it may, but it may not be the kind of optimization that you need, because if your problem is not in the CPU, having a faster compiler will not help you either.
Yeah. Thank you. Next question is, do you have an example case where you successfully implemented a custom DSL?
Well, of course, Brainfuck is not a real DSL in the sense that it's just a bit of a joke from my side to position it as DSL. I, for myself, don't have such an example.
Let's see, the next one. Is it possible to integrate the generated sources from Antler directly into my code, directly into my own DSL in TRUFFLE? Or does the source need to be annotated, etc. before use?
If you use Antler to generate your parser, then the code that Antler generates definitely needs to go into your component, because your component needs to be able to do the whole thing from parsing source code until executing it. And if the parser would not be present, then you can't have a complete runtime either. The source code that you're running, so in my case, the Brainfuck source code, well, that doesn't have to be known at compile time. The launcher that I also created in my project is actually a command line utility that just reads a file from disk and starts parsing that, assuming it's Brainfuck code, and then tries to run it. So the code that you're going to run does not need to be known at compile time, but all code needed to run it, you need at compile time, and you need to ship it in your component as well. I hope that answers the question, because I'm not exactly sure if I understand it 100% correct.
Yeah, we can ask on the commentary if it needs to be more clarified. Let's see.
That would be great.
If we don't care about Graal's performance, wouldn't it be easier to implement a DSL in Scala, Kotlin, or Haskell?
That's a very good one. And actually, I think implementing a language in GraalVM is typically not your first step when you have a DSL. I know about a Dutch bank, and they have a DSL that they developed in-house for mortgage calculations. That's a very complex domain, by the way. There's a few experts in the bank who know how to calculate a mortgage. And they had a hard time explaining that to developers. And that's why the developers came up with a very specialized DSL to allow those experts to do the calculations themselves. But if that's something that you do, say, 5 times a day with 10 people, then runtime performance isn't of that much interest. I mean, whether it takes a second or 10 seconds, does it really matter? If it's a job that you do a couple of times per day, it probably is not. And then it is way more logical to use, for instance, Scala or Java or whatever language to process those statements in the DSL and execute them, because that's more maintainable for you as the DSL maintainer. Doing this actually requires a lot of in-depth knowledge, and you need to keep that up to date, and you need to keep your implementation working. So unless performance is really critical, I would not say that GraalVM is the first choice for building your own DSL.
Let's see. The next one is, if we use Graal Community Edition and create a self-contained deployment with a trimmed down Java runtime, based on Graal, can we freely distribute it?
The first thing I should say is that I'm not a lawyer, and I don't really know. I recall having had this question when I did this talk on Code 1, like last year. And then a guy in the back stood up and said, well, I do work at Oracle Labs. It was actually one of the people that created Graal. And he said, and even I don't know. You should ask your lawyer. So they also said, a lawyer, I think you can, not sure. Please consult your own lawyer. I honestly don't know. I mean, that's not the situation I'm in. This is a pet project. I'm not shipping it to end customers just for learning and toying around. Well, then it's sufficient to say that you're not shipping it anywhere, and this is not really a concern to me. And if it were a concern to me, I wouldn't have made it open source, just to be sure.
Let's see, one last question. It was a bit unclear to me if the AST is just a result of parsing or if it also contains program state.
That's a good one. The abstract syntax tree is just a result of parsing. So given a piece of source code, I will always end up with the same abstract syntax tree. That abstract syntax tree is just another representation of what was already in the source code. And once I start executing it, then state comes in. And in the case of TRUFFLE, we use this virtual frame and the frame, what was it again? The virtual frame and the frame slot to interact with runtime state. Frame slot is the description of what we expect our memory to look like. Virtual frame, at least that's my 2 cents of how it works. There's probably a lot more to say about it. While virtual frame is the actual memory that I can work with. So to answer that question, the abstract syntax tree is just the program and it's not the data. The abstract syntax tree operates upon the data. That's when you execute it.
And that was our meetup for tonight. I wanted to thank everyone who have been listening to us and who is still live with us. I wish you have a safe and still a good evening. And Maarten, thank you so much for taking your time to help us out in this COVID-19 times. We really appreciated it. and a very interesting walkthrough and to listen to your experiences going through this hard work. And
you're welcome.
And I hope to see you next week with another edition of javaBin Online. So thank you, and have a good evening.